Hello again, everybody, and welcome back. We're continuing in Chapter 3 on vectors, and in this segment right here, we're going to talk about two things, actually. One, we're going to talk about what unit vectors are, and don't worry, it's nothing, excuse me, I'm moving my pen. It's nothing that's entirely new, it's just a new kind of you might say a naming convention or a new notation. The other thing we're going to talk about is how to identify certain types of vectors, whether they're position or velocity vectors, and then hopefully we'll finish up with a quick example, okay? So, here we are right here. So unit vectors are just like vectors, they're just named a different way. Let's say for a second that we have a, I'm going to change some of these X and Y arrows here a little bit too. Let's just say that we have a vector that is, looks like this. Okay, and it is 5 meters at, I want to say this is 36, we'll say 36 degrees above the positive x-axis, okay? And that's actually kind of steep. Actually, no, let's make that 53 degrees. 53 degrees of positive x-axis. There, that makes so much sense, okay? The reason I drew it that length at that angle is because that creates what we call a 3, 4, 5 right triangle. And so your y component right here, I'm drawing it kind of over top of the existing y component, and the x component are going to be 4 and 3 respectively. So there is going to be our x component right there, and that's going to be 3 meters. And the y component, I should have drawn that before, is going to be 4. Okay? So this vector right here, 5 meters, and we would write that full vector, so vector v, I'm just calling it that, vector v equals 5 meters at 53 degrees. It's 36 degrees from the vertical. 53 degrees, I'm writing everything backwards here. Sorry, above the positive x. Okay, so that's our vector in magnitude and direction notation. But if we were to write it in unit vector notation would look like this. The vector v, and here's where we're going to introduce x hat and y hat. These values right here, this and this, the x and the y, literally with that hat looking thing over top of them, we call them x hat and y hat just because it's easier. There actually is a technical name for these right here, but I think everybody, including students, are more comfortable with x hat and y hat. That just simply means that has that value in that direction. So, for this vector, vector v right here, we would write it in unit vector notation as such. It would have a value of 3 meters x hat, all right? And then we put a plus sign. The plus actually doesn't really mean plus. I mean, I guess you can think of it like that. But really, it means kind of like and. It's saying this vector has a value of 3 meters in the x hat direction and a value of 4 meters in the y hat direction. All right, that's it. This right here is our convention for, or is our notation for writing unit vectors. It just describes the vector in terms of its x component and its y component. So whatever is inside the parentheses is the value, and then x hat is on the outside, which says on the y-axis, and this on the x-axis, I'm sorry, and then the same thing for the y as well. 4 is the value, the y-axis is, the y-hat is the axis. So what this does is this actually allows us to draw, add vectors together a little bit more easily. So let's say, for example, and I just kind of showed you this right here. So it's whatever value x hat, and whatever value y hat. What if we wanted to add them together? All right, so let's just say, for example, I had, let's make this vector v from the previous page, all right? So I'm just going to turn that the a upside down, and that, okay? So that would be 3 meters x hat and 4 meters y hat, okay? And let's say we added you know, instead of renaming the vector, I'm just going to call it vector A. So it's the same vector from the previous page. I'm just going to call it, give it the same values. And then we're going to call vector B, we'll say it has the opposite values, all right? So it's got 4 meters in the x hat, all right? And it's got 3 meters in the y hat direction. Okay, so you can sort of see how these are going to be. Vector A is going to be like this, and vector B is going to be kind of like that if we base them off the horizontal axis, which would be right here, and there's the vertical. Okay, well, what would happen if we were to add them together? Well, we can add them together pretty easily by using this unit vector notation. Since it's already written in a notation that describes the x and y components, what we can do is simply write the sum of those two vectors, vector A and vector B. So if we say A plus B equals C, the sum of them would be the sum of the x values, x hat, and the sum of the y values, y hat. So if we were to add them together, I'll do this in green, all right? That would be, so vector C would be written 3 meters plus 4 meters, x hat, and 4, did I write that correctly? Yes. 4 meters plus 3 meters y hat. Okay, what does that simplify to? I'm going to write it up here. That's going to be simply 7 meters x hat and 7 meters y hat. Right? That's vector C right there. And that's the sum of those two vectors, vector A and vector B. Because we added together the x's and we added together the y's. And then we just write them in that notation right there. D would be opposite. D would be, well, not opposite, but it would be a very different vector if we were to subtract vector B from vector A. Because what happens is you subtract the x's. So it would be 3 meters, I'm writing this in purple, x hat, minus 4 meters. All right, so that would reduce to negative 1 meter x hat. My x's aren't looking quite like x's, so they look sort of like y's, but x hat, there we go. So D would equal this. And what's AY? Well, that's 4 minus BY is 3. So 4 minus 3, we can do that in our heads, can't we? That would be 1 meter y hat. Okay, so vector D would look kind of like that. Okay, vector C would be pointing kind of in the positive, above the positive x-axis direction. I'm trying to get a green marker right here. Here we go. Vector C would look sort of like that. All right, it would have 7 in the x, 7 in the y, both positive. Vector D would have negative 1 value in the x and 1 value, 1 meter value in the y. So that's unit vector notation. It's really quite simple. I actually probably talked about it longer than I should have, but it allows us to add vectors together easily because they are already stated in their x value and their y value notation. This slide right here is really just sort of a reiteration of what I just talked about. Okay. Now the next little segment right here, we're actually going to use unit vector notation to do this one example, but I want to introduce to you the idea of position and displacement vectors. Okay. So, changing gears just briefly, position and displacement vectors, remember anything can be a vector, any value in a direction can be a vector, but you can identify these vectors by their characteristics. R initial, which is this guy right here, okay, it is referring to a point that is some distance x and some distance y away from the origin. All right, so there's R initial right there. So it has some sort of x component and some sort of y component, but it is saying this is our beginning position right here. Okay, so that could be R initial, or it could be R final. All right, the final position, I'll do this in a slightly different color. I'll do this in orange. All right, has a different x component and a different y component, but again, it is referring to a different place that the object has moved to. Okay, so you can identify a position vector based on the fact that it refers back to the origin. It's saying this object is so far x and so far y from the origin, and this location right here is so far x and so far y from the origin. So, this vector that goes from the initial to the final, what do we call that? Well, you know what delta means. It means change, right? And any change in position we call displacement. So wherever you have a vector that is going from the end of one position vector to the end of another position vector, we're going to call that a displacement vector. All right? And it's really the difference between the final and the initial. And it's always true that the change in something is the difference between the final and the initial, but we can sort of prove it like this. Since these vectors right here are initial and change in displacement, or our displacement vectors, change in position vectors are tip to tail, we can say they're being added together. So we can say that our initial, this vector right here, plus some change in position, plus delta r, results in, now notice this is not put tip to tail with the previous two, but it's actually going from the original origin. Vector r final is going from the origin to the final position that the object is at. So those two added together result in our final position vector right there. So if we just do a little bit of algebra, we can say that our displacement vector is going to be r final minus r initial, like that. All right, so if we know this position and this position right here, we can find the difference, and it will tell you what the displacement is right here along this displacement vector. If we know displacement vectors, we should also be able to find velocity. Now, I apologize, my slide is a little bit messed up right here. But since displacement is a vector, average velocity should also follow along that direction. Because we say things like this: if average velocity, there we go, equals a change in displacement. Now, I'm not going to write delta x or delta y. I'm just going to write delta r. So we're just coming up with an imaginary axis right here. It doesn't have to be x or y. It could be anything. But it's just our displacement vector divided by our change in time. Time is just a scalar, so that means whatever direction this displacement vector in, the velocity must be in that direction as well. You can't move in one direction and have you can't be displaced in one direction and have a velocity in a different direction. Your velocity must be along that same line. So that's what this is saying right here. So for any value that connects 2 points, it's a displacement vector. That's indicated by our delta r right here. Okay? Position 1, position 2. And by the way, position 1 we'll do in red. So here's our position vectors saying, okay, there's position 1, and over here is position 2. Great. The vector that connects them is our displacement vector. But if displacement happens over a certain amount of time, we can say that a velocity took place, that there's a velocity vector. And of course, displacement will take place over time. You can't move somewhere else immediately. So depending on what that displacement is and what the time is, we can determine what that velocity vector would be in that direction right there. So quick one right here, and then we'll wrap up this segment. Okay? So we have a dragonfly with an initial position of this unit vector. So it's 2 meters x hat and 3.5 meters y hat. All right, and the final position is negative 3 meters x hat and 5.5 meters y hat. We want to find the displacement and the average velocity during this time. Oh, by the way, it takes place, it moves over 3 seconds, so there's our time right there. But let's find our displacement first. Okay, for delta r, in fact, I'm going to write 4 delta r for our displacement. Okay, we can say displacement, so arrow, equals the final position minus initial position. Okay, now we could set that up, that difference right there, using a vector table or a component table, but we don't have to because we can do that using unit vectors. So we can say it's the difference between the r initial x hat and the r final x hat. Okay, so what's the final minus initial x hat? Okay, so that's negative 3 meters minus 2 meters, right? Negative 3 meters. I'm not going to put the 0.00 because that's going to take up too much space. Sorry. Negative 3 meters minus 2 meters x hat, and the difference between the y hat, so that's going to be final y is 5.5 minus 3.5. 5.5 meters minus 3.5 meters y hat, and That's going to be our y hat value right there. So this is going to describe our displacement vector delta r. So what does this boil down to? Well, that becomes negative 5 meters x hat and 2 meters y hat. Okay? So that is the displacement vector of our dragonfly. Okay? So that's going to be our end of part 1. Now, it's written in unit vector notation, so that means it gives you the x value and the y value. We're not going to resolve them into the full value of the vector. I'm not going to find the full displacement, but you can do that. We would use our y value and our x value and the Pythagorean theory to find that, the Pythagorean theorem to find that. But we're just going to find the average velocity. And so since for average velocity, well, since average velocity, oops, reset, V average equals displacement over time, that means we can take our displacement unit vectors, negative 5 meters, excuse me, x hat, and our 2 meters y hat, and you may be asking, why did I make this parentheses so big? Well, we can just divide them by the amount of time that elapses. So that's 3 seconds and 3 seconds. So the average velocity written in unit vector notation is going to be negative 5/3, what's that? Negative 1.67 meters per second. We've got a new unit now because now it's velocity, x hat. And what's 2/3? That's 0.67 meters per second. That's going to be the y hat value of our average velocity. All right, so as long as we know the relationship between vectors, we can actually multiply them by scalars like time and convert them from displacement to velocity, and later on we're going to convert them from velocity, change in velocity, I should say, to acceleration. So that's unit vectors and vector identification. And in the next segment, we're going to be going a little bit further with that and applying this to velocity and acceleration. So if you have any questions, make sure you ask me. But in the meantime, thanks for watching, and I'll see you in the next one.